All right, let's get right into it. Have you ever wondered how we can actually know if one group is different from another? Like if a new diet plan really works better than an old one? Well, today we're cracking open the statistician's toolkit to figure out exactly how to answer questions like that.
So let's start with something a little controversial, a statement like this. Now, before anyone jumps to a conclusion, answering this scientifically isn't about opinions, it's about data. And more importantly, it's about using the right tools to look at that data in the right way.
At the end of the day, it all boils down to a really simple story, a tale of two groups. You've got Group A and you've got Group B. You measure something about them. The big question, the one we're always trying to answer, is this. Is the difference I'm seeing between them for real? Or did it just happen by random chance? And trust me, this isn't just some abstract academic idea. We ask these kinds of questions all the time. I mean, do you really get more done at work if you drink coffee? Do students actually learn better in a classroom versus online? These are real-world questions, and they all need a solid method for comparing two distinct groups.
So what's the first tool we reach for? Well, meet the independent samples t-test. The best way to think about it is like a precision scalpel in a surgeon's kit. It's incredibly powerful, it's accurate, and it's usually the first choice for researchers. And why is that? Because when your data is just right, this test is the most likely to find a real difference if there's one to be found.
So what is it doing, exactly? Well, the t-test zeroes in on the mean. That's just a fancy word for the average of two groups that are totally separate. For example, our online students and our in-person students. There's no overlap between them, right? They're independent. The t-test is what checks if the average score between those two groups is genuinely different. And that really gets to the heart of what this test is for. It's all about cutting through the noise to answer one single crucial question. Is the difference I'm seeing between my two groups a real thing, or is it just a fluke?
But, and this is a big but, here's the catch. Just like any high-precision instrument, the t-test has an instruction manual. You can't just throw any old data at it and expect it to work. For the results to be trustworthy, your data has to play by a very specific set of rules, or what statisticians call assumptions. So let's run through the checklist real quick. You need a random sample, the groups can't overlap, and you gotta watch out for any crazy outliers that might throw the whole thing off. But one of the most important rules, and honestly, the one that gets broken all the time, is that your data has to be what we call normally distributed.
Let's really zoom in on that one for a second, because it's a huge deal. This whole normally distributed rule is often the thing that decides whether our precision scalpel, the t-test, is even the right tool for the job in the first place. This picture says it all. Over on the left, you see that perfect symmetrical bell curve. That's normal data. Most of the values are huddled right there in the middle, around the average. But look at the right. That's skewed data. It's all lopsided, with a few extreme values way out on one side, dragging the average along with them. The t-test? It was built for the data on the left. So how can you tell if your data is normal? You don't have to guess. You run a quick test, like the Shapiro-Wilk test. It spits out something called a p-value. The easiest way to think about the p-value is like a traffic light. If it's big, greater than 0.05, you've got a green light. Your data is normal enough. Go ahead and use the t-test. But if that p-value is small, less than or equal to 0.05, that's a red light. It's a warning sign that your data probably isn't normal. And that leads us to the big question, right? What do you do when your data isn't perfect? What happens when you hit that red light and realize your data breaks the rule? Do you just throw in the towel? No way. You just reach for a different tool. If the t-test is our precision scalpel, then it's time to meet the Mann-Whitney U test. This is the rugged, all-purpose multi-tool of statistics. It's designed to get the job done in those messy situations where the scalpel just won't work. So the Mann-Whitney U is what we call a non-parametric test. That's really just a fancy way of saying it doesn't care about that perfect bell curve shape. It's the go-to choice when your data is skewed or when your data is based on ranks, like answers on a survey from strongly disagree to strongly agree. And this is where it's an absolute lifesaver. Think about comparing salaries in two different towns. If one town has a couple of billionaires, their average salary is going to be sky high, making it look like everyone is super rich. A t-test would be totally misled by that. But the Mann-Whitney U? It's smarter. It looks at the median, the person right in the middle, which gives you a much more realistic picture. It's the perfect tool for the job anytime you fail that normality check. Okay, so we've met our two champions.
the t-test, and the Mann-Whitney U. Let's wrap this all up in a simple guide so you know exactly which tool to grab from the toolbox and when.
Here it is, a side-by-side showdown. Your t-test is the precision scalpel. You use it for continuous data that fits that nice bell curve, and it compares the averages. Your Mann-Whitney U is the rugged multi-tool. It can handle continuous data or ranked data. And this is the key. It does not require normality. Instead of looking at averages, it compares the medians or the overall ranks, which makes it awesome for dealing with outliers. So if you remember just one thing from all this, let it be this. The most important step isn't picking the test itself, it's checking your data first. You have to understand what you're working with. That one simple check is what tells you whether to reach for the scalpel or the multi-tool. It guides the entire process. So there you have it. You now have the basic framework for comparing two groups the right way. You know what to look for in your data, and you know which tool to grab to get a reliable answer. So the only question left is, what differences out there in the world are you going to investigate?